So, today is which session for you for embedded learning? Which session? Okay. So, tell me, what was your first session about? Machine learning and? That's it? ANN. Basics of artificial neural networks. What was your session, second session, theory session here that you are doing in auditorium? Third one, ANN, no. ANN plus? ANN plus? Achha, you are, okay. You have done first ANN, first basics of machine learning, then basics of ANN, CNN, and then RNN. Okay. So, what was the disadvantage with ANN when it comes to image data? Okay. And yes. Then in what sense CNN helped with an image data? Okay. And very important. What does it do? What does a convolution layer do? It helped you to extract spatial information that we call as locally correlated data. Correct or not? So, images give information not only about a single pixel, but about its surrounding pixels also. So, you required certain specialized network to perform such operation and extract features. There were two uses or the two benefits that I can say. One was locally correlated data was very well easily extracted layer by layer using convolutional layers, followed it up with a pooling layer, but of course, yes. And second was the dimension of the data was so big. You wanted to reduce it before you wanted to give it to a normal feed forward or feedback, normal ANN. Okay. So, that particular mathematical calculations were all done by a convolutional layer, extracting features from a given image of higher, not one image, right, multiple images. So, imagine the amount of data that you have got. Okay. So, multiple images of very big, huge number or huge size of pixel dimension also, you were able to reduce it without removing any specific important information or features out of it. Okay. So, that was the benefit of using a CNN model. What was the drawback of CNN model? What type of data it could not handle? What I want to hear from this side also. What type of data could CNN not handle? Okay. And there's a term for that type of data? You are there. Sequential data. Okay. So, CNN was not able to handle any data that was dependent on time or in other way which required some amount of memory to it. Okay. So, sequential in the sense one after another. How would you know that previously this was there and then the next one should come? So, there has to be some amount of memory requirement. So, whenever the data was working on timestamps, CNN was not in position to handle it. So, thereby we got another neural network into picture. What was that? RNN stands for recurrent neural network. Why it is called recurrent? So, what is a recurrent layer? What is happening inside a hidden layer? Hidden state will be there. Correct. So, now see what is happening inside an RNN in a brief I am going to tell because a lot of it we are going to learn today. So, today the topic is long short term memory. Okay. So, the background check I am going to talk about a little bit of drawbacks of RNN. So, before going to that I am telling a bit on RNN. You all know RNN is used for sequential data like text, sequences of images, any sequential data. Okay. RNN will be useful for. RNN has got one specific difference when we come to a normal neural network, RNN architecture. Could you Recollect that? Could you recollect what specific feature an RNN architecture had that was lagging both in CNN and ANN? Very good. So there was a feedback present in an RNN. What was that feedback for? Hidden state, okay. But what was that feedback for? So as we told sequential data, you required some past output what was there to calculate the what is next in the sequence, right? So for that reason that feedback was provided. Clear enough? Right. Now that was about RNN. You have read and dealt pretty much good about RNN. Now today I am going to start with, as I already discussed, what are RNN, recurrent neural networks. So as you could see the diagram over there, you are taking any sequential data X as an input and you are predicting an output Y, but you can see that input is defined or it is dependent on time, so it is denoted there as X of t. Now from now onwards, it will be, at every time step, at every sample of that sequence, we will call it as X of t. Anything previous is X of t minus 1, anything next is X of t plus 1 and so on, correct. So RNN process sequential data where the output of one step is fed as an input to the next step. So this already you have seen and covered in an RNN. So today I am going to talk about what are the challenges with RNN. Now from here onwards, you are diving towards NLP. Today's session is very important. Kindly concentrate and you are welcome if you have got any sort of doubts or questions. Okay. So if you have very well understood RNN, then only you can understand this particular part. See, everything here is in a loop. Everything is sequential in this particular session also. Please do not miss the session. You will not understand the next session. Okay. This is also sequential. So now I am talking on challenges faced by RNN. So as I told, RNN overcame the disadvantage of CNN and ANN that it could process data that was sequential in nature, correct. But it had certain challenges like exploding gradient descent and vanishing gradient descent. Now what is gradient descent? What is gradient descent algorithm? Where do you use it? Back propagation. Why do you use it? To update your weights and biases. What for? To reduce loss, optimize your output, whatever you are getting, reduce the loss error and get an optimized output for that reason. Okay, could you recollect what is the formula for updation if at all I want to update any parameter like weight? What is the formula associated with gradient descent? If suppose I am updating a weight, new weight is equal to old weight minus learning rate into gradient, correct or not? Yes or no? Yeah, everybody, how many of you are okay with that formula? Good. So now what am I talking here is about that gradient descent part. Now you are doing lot of mathematical calculations here in these type of neural network. So there could be places where that gradient that am I discussing goes very big, it is huge enough. So when I am telling new weight is equal to old weight, say suppose if I am updating weight, new weight is equal to old weight minus learning rate which is into the gradient. So what if that gradient is very big? New weight will be very much different than what was the previous weight. So there is huge amount of gap for updation. Understanding? That is called as exploding gradient descent. You cannot go for that much big change in the updation of your parameters also. That is also one of the drawback. Okay. Second type of drawback is called vanishing gradient descent. Now before coming to vanishing gradient descent, which is actually very, very crucial here, exploding gradient descent to an extent can be eliminated by using a suitable activation function. I place this question to you. You have already read several activation functions. Could you name a few? ReLU, sigmoid, TANH, softmax, right now? Now remember this. What I am telling here, exploding gradient descent problem I told you. I am giving solution also. It can be overcome to an extent by using a suitable activation function in RNN. What is that activation function? Very good. TANH. Why? Okay, we will get back to that. Okay. So, what is the next problem that we have got? Vanishing gradient descent. Very, very important concept. Okay. So, what is happening in vanishing gradient descent? The very first thing. What is exactly the flow of information throughout your neural network? There is a feed forward, then there is a feedback. If you see from here, and there is a feed forward, wherein you just add your weights and biases, calculate your output, and then what you are going to do? Calculate the loss backwards and start updating weights and biases. So, which layer weight gets updated first? Last. Yes or no? Yes or no? So, backward propagation means you will start learning from backward towards front. So, back layers gets learned first, then comes the first layer. Now, imagine what is the formula that you are working? New weight is equal to old weight minus learning rate into gradient. Gradient eventually is diminishing. Starting it is okay, eventually it is diminishing. Diminishing means coming towards 0. Okay. So, earlier layers backside, they will be updated. Say outer layer 1 got updated, outer layer next got updated. Slowly, slowly, gradient became 0. Gradient became 0. So, what happens to the formula? New weight is equal to old weight minus learning rate into. So, new weight is equal to. Any learning happening? Any learning happening? So, there is no learning happening in your network. There is no change in the weight. Whatever you do, there is no change in the weight. That means same output will be getting predicted. There is no optimization in your network. Understanding? There is no learning in your network. So, that is one of the biggest problem of RNN. It tells you if your text size, understand, text size that you are giving, input size to an RNN is short, then fair enough, learning happens. It is able to remember. If the sequence of information you are giving as an input is too large, what happens? Vanishing gradient descent problem, and it will not remember. So, in other words, if I want to say in your language, RNN is like Gajini. What is it? What is the famous phrase associated with it? Short-term memory. Yes or no? RNNs are actually having a short-term memory. Clear enough? Why? Major problem is your vanishing gradient descent. Okay. So, see, nowadays we have got humongous amount of text data that is available which you want to process, right? So, imagine if you are using an RNN. You may not, see, I am not telling it will not give you output. It will not give you much optimized output because learning is not happening. You will not get accuracy in your predictions. See, where are you using all these applications? For an example, Google. You know, you just type a few sentences, it predicts you the new words. So, how can you do when you are typing a very long sequence? So, we had to overcome this problem. Okay, exploding gradient descent to an extent can be managed by some such solutions, but there was a lot of problem with vanishing gradient descent, and that was directly affecting towards your learning capability of your model. So, how did we overcome that? So, before going to that, a little bit more, why actually RNN fail for long sequences? Please have a look carefully. Generally in RNN, earlier layers of network don't learn much due to vanishing gradient problem. Correct na? As I told, outer layer learn first, then slowly comes to the initial layers of your model because we are doing back propagation. So, as gradient is diminishing, Learning is not happening in the initial layers of your model. Okay. So this leads RNN to forget and thus have a short-term memory in long sequences. RNN cannot retain long-term sequences in the memory. So there was a new type of neural network which was an enhancement of RNN that was introduced, that we call it as LSTM, long short-term memory. Okay, LSTM. So that was introduced to overcome this problem of RNN. What did it had? It had a certain special architecture which constituted memory cells, which constituted certain gates. Gates means what? Why are you using gate? Why do you use gate? To come in or to go out. So here also LSTM has got gates to regulate that information. Which one has to be stored and which one has to be discarded. Just a gist I am giving, we will dive in detail. Okay, so LSTM introduced gates to manage the memory and to handle long sequences effectively. So that was the solution for all the challenges that RNN faced. Now, to make it a little interesting, I have a question for you. Why do you think memory is crucial for handling sequential data? Anybody?
Because one depends on the next.
Yes. Anybody from that end? Question? Why do you think memory is crucial for handling sequential data? Okay. Yes. Okay. So, now, next question. What is the difference between recognizing a word and understanding the context of a word? What do you understand by that? I'll give you one example. English sentence. Okay. The movie was good, not bad. The movie was good, not bad. How many words? 6 words. Identified all 6 words? All 6 words. The movie was not good but bad. Same words? Context is same? Context is same? Yes or no? So tell me now, only recognition is important or understanding context is important? Understood. So movie was good, not bad. So that's a what type of sentence? What type of feedback? What type of sentiment? Positive. The movie was not good, bad, comma, bad. So you can see how a typical change in the position of a word, you got the entire meaning of the sentence changed. Now you understand why sequence of the word is important? Yeah? So now you understand why memory is important. So it is just not that. To really understand the context of a particular sentence, it is very important that you understand the sequence of words in that particular sentence. Clear enough, guys? Now, recognizing words is straightforward, but understanding the context requires memory of previous words. Yes or no? Where was not coming? Where was good coming? That was important for us. This is where LSTMs excel. Thus, memory cell is the requirement. So, this is the reason today that we are learning about LSTM to give an enhanced version of RNN. Clear enough? Now, one more example I'll tell you. What is the need for LSTM? So, if we are using any traditional RNN, we will have a look at that example. I'll read that for you. It is like a typical prediction of next word model. So, I am giving an input to RNN. The sky is. What would be the prediction? Blue, of course. So, give it to a simple RNN. The sky is blue. It's just a 3-word sentence. It is going to definitely give you a prediction because I told it can understand short-term memory. It can retain it for short duration of time. Clear enough? Now, suppose I give another example. Now, what did I put in that sentence? Krishna lived in India for 12 years and he loves watching movies. He's a fan of dramas. He is fluent in dash. Predict. Krishna lived in India for 12 years. Blah, 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 blah. He is fluent in? You predicted, no? Hindi. Why did you predict? You remembered the first sentence. What did the first sentence say? Krishna lived in India. Had you given it to a traditional RNN, it will not predict it will predict, but it will not predict correct output because it does not remember that first sentence. Are you understanding this? So this is the reason you require LSTM. So the reason of failure for RNN was long-term sequences, and there was an inherent relationship between those sentences. If you can relate Krishna to India and to some other thing, then you are asking about language. Then you can predict what is the next word. So that was the major problem with a traditional RNN network. Okay, now solution was LSTM as I just discussed. Now another question answer. Please read it. So how do you determine to buy something online? I'm sure many of you do a lot of online shopping. Very good. What is it? Reviews. Reviews. Okay. So if you talk about me, there will be like thousands of reviews present across, say, Amazon. Okay. So if I'm buying something, there will be one heading to that review. Yeah. And then an entire big paragraph. Do you have such patience to go through that? Generally, how do you go for a review? How do you read a review? Okay. If I'm talking on textual review, check the first line, or if first line is not given. No, I'm talking about text review. So generally, you will read the review that you want to buy. That was the answer, correct, that you have given. And you will remember some important points in that particular review. Let's say very good, beautiful dress, bad movie, if you're talking about review, movie review, correct or not? So some basic, words that could actually give you about the quality of that particular product or about that review. You will filter out the remaining the, a, and. Do you go through that? No, you will subconsciously scan for these words and then you'll come to a conclusion that whether it is good or not. Yes or no? Yeah. So, the words that you will concentrate more are on the, like say, bad, poor, good, better, amazing, and you will not concentrate much on the words that are insignificant, like a few that I have listed over there, they, should, the, a, like, etc. Okay. So now, when recalled, you would remember all the keywords and tell the feedback. Yes or no? So, if you have read some, say, 10 reviews, and you are now suggesting that particular product to your friend, do you remember that a, and, but, what has come? You would just give an overall conclusion. Okay, this is about this product, it is amazing, everybody told it is best for its quality, very good in the price, just like that, all those keywords only you will recollect and you will tell. You will not be remembering entire text to text what was there. Yes or no, guys? Please interact. Yes or no? Yeah. So that is what LSTM is doing. Try to understand. The name of LSTM, what is the full form of LSTM? So there's a short-term memory, but a little bit of long. So now you have to understand that the entire big corpus that you are giving, or a big amount of text that you are giving as an input to an LSTM, it will not remember everything. It will remember a few keywords from the, previous sequences of samples, and then it tries to predict whatever output that is going to come. Clear enough? So the same example that I've just told, how your brain is working, in the same way LSTM also works. That's how the name is long short-term memory. Still it is an RNN in calculation of hidden state. But apart from that short-term memory, it has got a bit of long-term memory that is going to give you better accurate outputs when compared to a vanilla RNN architecture. Clear enough, guys? Yeah. So, LSTM, how does it do it? Like till now we have seen it is doing like this, but how does it do it? So it has a mechanism with the gates. So I just gave you a little briefing on the memory cell and the gates. So I told now you require to store certain keywords now. Keyword, what is keyword technically? Long-term memory. Clear enough? So it requires some memory cells inside it and also to regulate. See now as I told, the movie was good. The discarded. Movie has to be kept because that's what the subject of the sentence. Was, no need, discard. Good, okay, some sentiment is there. So movie, good, like that. So you are trying to filtering out certain information. You are trying to retain some information. So there has to be some mechanism. How do you do that? There is memory to store that keyword. Okay, memory cell is the requirement. But how do you do that? Remove something, add something. How do you do that? So you do that through gates. That is the gate mechanism. So LSTM have mechanism with gates which can regulate the flow of information, which recognizes which data is important to keep or to discard, which uses relevant information to make your predictions. Now, so LSTM, from now onwards, why are we learning this? Because from now on we move into a bigger picture of NLP and then transformers, okay? That is actually, you know, the aim of this particular program that has been introduced to you. So we will quickly look into a basics of natural language processing applications wherein you will be using LSTMs. Okay, so NLP stands for, you already know, natural language processing. What do you understand by that? What do you understand by NLP? It should not be restricted to text. It can be voice also. Voice also is a sequence, no? Okay. Next. Tell me, what do you understand by NLP? Anybody can tell me in your own language. I'm not asking for a definition here. Human language. So you are trying to interpret, you are trying to work on several applications based on natural language processing. Now, I have listed a few here. Let's see. The first one is spell correction. We all use this? Yes or no? We are use this or not? MS Word, MS PowerPoint, everywhere we are using a spell correction. So, as per its NLP model, it predicts what exactly should be the word, what are you writing. If it is mismatched, then you will get an underline there. Yes or no? That is one thing. Second is machine translation. Nowadays, you know, if you just go back 2 to 3 years back, I don't think Google was able to do this. You know, you just had to type an entire full sentence. You were not, it was not predicting what sentence you wanted for what is the next word. It also was not translating that into any other language. But today, as soon as you type a few words in Google, it starts predicting the next word. It, as you press the enter, it tries to translate that for your own language, starting from Chinese, Japanese to our regional languages as well. So what exactly is it? It is the biggest application of NLP here. Okay, so language translation, the machine translation, here we are trying to, you know, convert your text or your speech into natural language or any other language that a human can understand. So machine is able to understand your language also. Okay, so that is one of the important applications of NLP. Then you all are aware of this application. What is it? Chatbot. Every app nowadays has got a chatbot wherein user relevant queries are answered to whatever you know, answers that are present in its database. So it has to understand the context of what a user is asking. Based on that, it has to give the solution that is present inside the database. Yes or no? Right. Next, very important, we will be doing exercises also on it. What is it? Sentiment analysis. What do you understand by sentiment analysis? What do you understand by sentiment? Sentiment means emotion. So, with every text is an associated emotion. Yes or no? It could be a happy sentence, a sad sentence, a good sentence, a bad sentence. I mean, I'm talking about the emotion that is associated with it. Yes or no? So, sentiment analysis is known as opinion mining. Using sentiment analysis, lot of apps can be, it helps, it is just like a feedback that you take, so that even after my session, I would be asking you several things in my question. So your opinion actually matters to me. That is what I am doing, data, opinion mining from you. How many of you actually liked the session? How many disliked? How many of you think there was a scope of improvement, so that our next session is getting improved? So sentiment analysis is a very, very important application. Using the text or the voice, converting that into a positive sentence or a negative sentence for helping and improvising your product. That is where you use it, okay? So it helps you to analyze attitude, behavior and emotional state. So this application is implemented where you combine NLP as well as with the statistics which are associated with the text. So here as an example, I am taking 3. You can see a big smiley. That means it is a positive sentiment which is associated with a certain text that you have given. The other one is a neutral, neither positive nor negative. The movie was okay, okay. So if I write movie was okay, okay, it's a neutral sentence. Okay, the movie was fantastic, positive sentence. The movie was horrible, negative sentence. So given any text or a voice, you want to determine what is the sentiment associated. Based on that, you start that rating. You told, no, when time is not there, we will not see those reviews, we will watch that rating. How is that rating coming? 5 stars means superb. 2.5 stars means neutral. 1 star or less than 1 star means poor. So that entire review will be taken, given for opinion mining. Based on the sentiment classification, that rating will be given. Clear enough? Yeah? So that's a very, very important application of NLP. Next. Many of you know this, but you don't know that it is actually a part of NLP application. So if I am waiting to receive an important email from something and you don't receive it, and you call your friend and he says, "Arey, spam mein check kar, spam mein check kar." Yes or not? So what is happening? All your mails are actually automatically classified into a spam or an inbox. Okay, spam or non-spam. How does it do that? It is also an NLP application. All the texts go through the inbuilt NLP model of your Gmail or whatever mail that you are using, and it tries to classify based on that as a spam or a non-spam. Spam goes to spam folder, non-spam comes to your inbox. So how is it possible? Through this NLP model only. Clear enough? If I give it to RNN model, will it classify properly? Why no? You should first ask me what should be the length of email. Even with RNN, it is possible to do sentiment analysis. But you will first have to ask me what is the length of my mail. If it is a small sentence, then yes, why not? If it is a bigger text, then you have to go for LSTMs. Clear enough? So bluntly, don't give me that answer, RNN cannot do. RNN can also do. It is actually a wonderful tool, that particular neural network, but it has its own cons. Okay. Now, next is text summarization. Very favorite today, na? ChatGPT is also one of the NLP applications only. Very favorite with you or not? So passing on that entire 300 pages of PDF 2 days before exam, getting the summary out of it. How many of you could relate? Yes or no? So that text summarization that you do also is an application of NLP, wherein the entire huge corpus you study and you just summarize important points and it gives you as an output. Clear enough? Now we will quickly dive into today's major topic, that is about LSTM. Till now you have just seen a briefing, a wrapper. We will now dig into the technicalities of LSTM. So LSTM stands for? Why are we studying LSTM? What was the disadvantage with RNN? First one? Okay. And second one? What happened with vanishing gradient descent? Short-term memory. Short-term memory was there in RNN, right? So that's why we are going for LSTM. So long short-term memory is the full form of LSTM. It's an artificial recurrent neural network only. It is an enhanced model of RNN. It is an RNN, yet an enhanced model, okay? So it's an artificial recurrent neural network architecture which was proposed in 1997 by Sepp Oeschritter and Jürgen Schmidt-Huber. And unlike any standard feed-forward neural network, LSTM also has got feedback connections. That's the reason I told it's an artificial recurrent neural network. I didn't state it as an artificial neural network. I told artificial recurrent neural network. That means there are feedback connections that are present inside an LSTM. So it can process not only single data points but also entire sequences of data such as speech or video. So even video processing, suppose an example application, if you're going for video captioning. So video is nothing but a sequence of images. Yes or no? So, assessing that, getting a summary out of that video or video captioning, all of these, apart from CNN, you will be also using RNN. So, it's a combination that works there. So, there are several applications where both of it goes hand in hand. But wherever you are working with sequence, at that place you will be using either RNN or its enhanced version like in LSTM. One of an enhanced version of an RNN is also GRU, gated recurrent unit. It is again an advanced version of LSTM that we are not seeing. Majorly we will see from now onwards all these applications of your NLP using LSTM. Okay. Now, this is the internal structure of LSTM. What you are seeing onto the screen is actually called an LSTM cell. So you can see a little bit of internal structures over there. As a brief, now I can tell you that it is a memory cell and it has got what? It has got gates. I told you this, right? So there are three types of gates actually in an LSTM. First is an input gate and an output gate. Yes, for sure. There is a third gate also which is called as a forget gate. Okay. So input gate controls what information is flowing in and out of that LSTM cell. Yeah. Forget gate helps to understand the cell which information has to be forgotten, which information has to be retained. Okay. And there is an output gate which controls which information is supposed to be output out of that particular LSTM cell. Each and everything we will see in major, in a very detailed form in subsequent slides that are coming. Okay. So, apart from that, I told LSTM is in RNN. Okay. So, RNN mein what is the most important part that actually calculates the next output? Hidden state. So, hidden state is also present inside an LSTM because LSTM is an RNN. So, that short-term memory is coming from where? Hidden state. Clear enough? Three gates, input gate, output gate, forget gate, hidden state, which is going to give you that short-term memory with which you try to predict your next layer output. Okay. Hidden layer is obviously, hidden layer when I talk. Do you remember from RNN? What is hidden state dependent on? What input does it take? What input does it take? Previous output and present input. Previous output नहीं, previous state बोलेंगे. Output is something that we are taking actually at the end. ये intermediate output है. So all these intermediate outputs you call them as states, or from one layer to another layer that you are determining, from one cell to another cell that you are determining. So previous state. So if hidden state is denoted by h of t, then that timestamp output is y of t for an example, and current input is x of t. Okay. So you are calculating for that timestamp the output state h of t. What it is dependent on? H of t minus 1 and current input x of t. See, that equation from RNN will come throughout. Please remember. Okay, please brush up before you come. See, all the topics are like, in sequence. Please remember your previous topic while you are coming for the next class. Okay, so that y of t will be dependent on h of t minus 1 and x of t. The same case works with LSTM. LSTM uses a hidden state which is updated based on input and previous hidden state and memory cell's current state. Now, please understand this. You might have heard about embedding layer. How it is actually being processed, that we are going to see today. Okay, so word embeddings actually helps the machine to understand the words or the sequence of the words in a particular text or a sentence. Okay, so what is happening? Suppose if I am talking on RNN only first, then the words will get transformed into machine readable vectors. How is that happening? That is called as a typical text pre-processing that you perform before passing on these vectors to any RNN model or LSTM model. So you can understand this embedding layer as a wrapper that is being present before you give it to any RNN model or an LSTM model. This text pre-processing is very, very important, wherein what you do, you scrape or collect your data, you label that data, normalize that text. Very, very important is that vectorization part. So vectorization that we are going to see today, and then it is given to a particular model. Clear enough? Any sequential model that you are working on, that is your text pre-processing steps that you have to follow. So given now that in your exercises will be giving you what is the input. So it's already scraped. So there is input that is present to you. You have to perform that word embeddings for me. That is, you have to perform that vectorization part before you actually make that data ready to work with your any sequential model like an RNN or LSTM. So what are these word embeddings? The word generated on each timestamp is a character and not a numerical value. Agreed? Yes or no? So these neural network cannot process directly any string data. Yes or no? Right. So now conversion of these words or characters into numerical values become very critical in neural network applications like NLP, because majorly everything is a huge amount of text or voice, whatever sequential data it is. You have to convert that into machine readable format. So what is that format? Through word embeddings, you are finding a way to represent the words as dense, continuous valued vectors in a fixed dimensional space. Okay, so try to understand this. Machine understands numerical values. You are trying to convert the words in your text, whatever you are giving as an input, to be converted into machine readable vectors. That is called as word embeddings. Are you clear with word embedding? Yeah. So there are several ways of representing these word embedding. First is a space representation. Next is a dense representation that we will talk on. Space representation, indirectly I have already learned throughout till now. The very first that I am going to talk about on space representation example and very popular is one-hot encoding. You have heard about one-hot encoders or one-hot encoding? Yes or no? No. Okay. So I'll tell you. What happens in a one-hot encoding is, it is encoding. Encoding means what? Converting one form into another form. So suppose if I want to represent, say 4 countries are there in that example, Rome, Paris, Italy and France. I'm going to represent that as machine readable vectors. So how many words are there? 4. Now first I have to understand what is the length of my vector. I'll tell you, the length of the vector is always fixed and it is always defined by the user. So you will be deciding what should be length of your vector. So one more important point, very, very important, please note down. This length of the vector is your hyperparameter in RNN or LSTM. What was the hyperparameter you came across in ANN? Hyperparameter in the sense, indirectly it is affecting your model's performance. Do you remember in your ANN what was your hyperparameter? Parameters were weights and biases, no? What was your hyperparameter? Learning rate, somebody told. Okay, so learning rate was your hyperparameter. Are you not using learning rate here? You're using. But there is, you are doing the same forward propagation and backward propagation here also. But apart from that, you are using that embedding layer now, in that you are fixing that vector length. That vector length again is a hyperparameter. Your performance will be dependent on your size of the vector length. You could ask me, why, ma'am? The bigger the length of your vector, the more will be your computations. Taking bigger vector length will accommodate lot of your, where was I? So I was telling you, how do you fix that particular vector length? Suppose if you take it too large. When you take it too large, of course you can incorporate lot of sequences of words into your particular input. But then you'll have to think how much amount of time the machine is going to consume to perform those heavy computations. So if you are okay with time, but you want accuracy to be more, you can fix better, large amount of vector length into your embeddings. But no, you want pretty okay accuracy, but your time also matters. Then you will have to work on the dimension of your vector. Clear enough? That's how this particular part is a hyperparameter in any model, RNN model or LSTM model or any other models that you're working in sequence. Okay. So, one-hot encoding, what does it do typically? Let's say here I have taken 4 words, Rome, I have taken Paris, Italy and France. Let's say I have decided my vector length to be 10. Okay, so now for every word, one-hot encoding will take a significant position of 1. Okay, let's say it starts from MSB side. Okay, so for Rome it starts like 1 and all zeros. Okay, for Paris, first position of 1 is already taken by Rome. So 0, next position, next significant position of 1 and then all zeros. Okay, and then Italy, 0, 0, 1 and all zeros. So like that in the sequence. So you can imagine if it is a little bit of words in a sentence, it works. But then if you have a huge corpus of data, how is it going to work? It is going to take lot of memory, isn't it? Yes or no? So that's why we generally don't use one-hot encoding here in RNN or LSTM model. So that's called as sparse representation. One-hot encoding vector is a high dimensional and extremely sparse with a large number of positions as zeros. So it is computationally expensive. How can I say it is computationally expensive? More number of, the length of the vector becomes too large if you have got large amount of text input. Okay. And it is also not conducive to neural network training. Also, it ignores semantic relevance inherent in the words. Very, very important. So, what is this semantic relevance? Here, all these words are taken as different entities. So, now what happens in dense representation? Why do you go for dense representation? Is each word is represented as a vector. Let us say we define it as 100 dimension. And these vectors are learned in such a way that semantically similar words are close to each other in the vector space. So you are not bothered about here significant ones or zeros. We give random vectors initializations, but we make sure that the word that could be near to that particular word in meaning, in semantic, will be kept closer to it, so that fetching and doing your computation is more easier when compared to your one-hot encoding. Clear enough, guys? So here I kept one example there if you can understand. Like if it is man as a vector, that woman as a vector would be kept closer to it. If it is king, then queen will be kept closer to it. Are you understanding? Why, you can ask me? Because suppose if I am asking a model to predict me the next word, then let me say that he is a king, full stop, she is a dash, queen. Because they are semantically connected and they are closer to each other, they are kept, predictions become very, very easier. So what do you understand? When you undergo word embedding with semantic relevance, you are clearly understanding context relevant to your sentences. Agreed or not? So that's what is your importance, no? Context relevant predictions you require. That is the reason we go for dense representations while designing your embedding layer. So now there are two ways in which it can be done. One is you do everything from scratch. You initialize all of them randomly, create your own lookup tables, or you can use ready-made, pre-trained vectors. Okay, these days though, all we do is we use pre-trained vectors because the data size is very, very high. You cannot build everything from scratch. So, importance of word embeddings that we talked about, it could capture semantic similarity, dimensionality was reduced, it could help you to understand the context of sentence better, and then it is used in transfer learning, etc. and etc. Okay, so this was the importance of word embeddings that you have, learned that particular concept today. Now, we'll see now how these word embeddings actually work. Concentrate. We are going to do an exercise today on this. So here I am telling a few steps, few only, remaining all steps I'll teach you when I'm teaching you that particular exercise. Basic ones I am teaching you here. So how does embedding layer work? The very first thing that you go for, the first step is input tokenization. What is the first word? First step, input tokenization. So what are you doing in input tokenization? Here what you will do is, you will try to create vocabulary of unique words present inside your text that is given as an input. For an example, if suppose I am telling here, I am happy today. So it creates a vocabulary, creates a set, I am happy today. It breaks it down and creates its own vocabulary, and then it assigns indexes to it. Indexing starts from 0. So I will be assigned 0, am will be assigned 1, happy 2, today 3. Okay? Understood? So like that. The first step is what? Input tokenization, where you will tokenize all the words that are present inside your text, and you create a vocabulary, and then you start assigning indices to these particular tokens. Okay. Next is what? Embedding lookup. So embedding lookup is what? Very, very important, guys. You create a lookup table. What is a lookup table? Any idea? Lookup table is like a matrix. It is like a matrix wherein your rows will be of the tokens that you are extracting out of your text. All the words. And then in the column what you will have? The vectors that you will frame for them. Okay, number of columns will be equivalent to the number of vector length that you are choosing, that a designer is choosing. Are you clear enough? Right. So embedding matrix or embedding lookup is of the size. What would be the size? Can you tell me? Try to understand what is there on the row side. How many words are there in your vocabulary right now? Okay, so vocabulary size. Vocabulary size will be there, and by what will be there? By what will be there? The dimension that you have chosen for your vector. Understanding? So say if I am saying today, I am happy today, and let's say you should ask me, ma'am, what is the vector length that you have chosen? So let's say I have chosen a vector of dimension, say 50. So 50 should be my vector length, and how many words I am telling? I am happy today, say 4. So what should be my embedded matrix dimension, guys? 4 by 50. Understood? So lookup table. So whenever in my other context, if I have this in my memory, in my subsequent text, if I am facing happy somewhere, then immediately happy, embedded matrix location 3, what is the vector? It's going to fetch. Now, relevant to happy, I am going to put it somewhere in 2 or 4. Are you understanding? So somewhere near, semantic relevance near, and I'm going to fetch predict the next word based on the context. Based on the context. Few examples we will see, you will understand. Okay, as of now, are you clear with this step, basic step? Input tokenization. You tokenize your text data, create a vocabulary, provide indexes to it, and then you fix a certain dimension to your vector and create an embedded matrix out of it. Are you clear? So the same example that I told you just now. Example sentence, I am happy. So I am first tokenizing it. I separate am separate happy. So how many tokens are there? 3 tokens. Are they unique? Unique means not repeated. Yes. Okay. I am providing their indexes. I is given 0, am is given 1, happy is given 2. So what is the length? Overall length minus 1. 0 to overall length minus 1. And then say for a vocabulary of 10,000 words, if the embedding size means vector length. Okay. If the embedding size is 100, then the dimension of an embedding matrix will be 10,000 by 100, let's say. That's just an assumption. So we will create, suppose if you want to retrieve the vector for a word, say happy. So happy falls into what particular index? So happy is not fetched. Embeddings of 2. Can you see there onto the screen? Embeddings of row number 2 is nothing but happy, and then you have a vector length. So wherever you have got a semantic relevance where you are predicting something related to happy, it will extract that particular vector and then gives you your output. Clear enough, guys? Yeah? Now, so as I told you, there are 2 ways how you can actually create this embedding matrix. Either you do it from scratch, randomly initialize and create your own embedding matrix, or you can use pre-trained vector packages that are available nowadays like FastText, Word2Vec, Glow, etc. many more. Okay, so as I am referring here, embedding size is a hyperparameter. Let's say you take it as 50, 100, 300, etc. If you are taking it for a larger dimension, it will obviously, able to capture large amount of information, but computational cost will be there. It will take large amount of time to compute your output because, the size will be big. And input to an embedding layer is a batch of sentences with word indices. See now, it is important here in our applications of LSTM. Had it been an RNN, I would not be talking much about batches. Okay, but because now we are using LSTM, so there will be lot of sentences that you are giving as an input. So all these sentences also go as batch. So apart from now your words, what exactly will you have now? Batch numbers associated. It's very important, guys. Please understand. Okay, so batch of, let's say, 2 sentences of 4 words each will be something represented like that you can see onto your screen. This light is not working. If you can see over there, what is it? It is like a tensor. Okay, so you can see there are two batches of 4 words each. So indexes, not representing words here, I am writing their indexes. Okay, in 0, 1, 2, 3, that is first batch of sentence with 4 words. And then 4, 5, 6, 7, it is second batch of sentence with 4 words. So that's how will be the representation. So whenever you are printing an output for such application, such programs, you will see the output would be a 3-dimensional tensor. Output would be a 3-dimensional tensor, wherein the first dimension will be talking about the batch size, second will be talking on sequence length, and the third will be talking on embedded dimension. So till now what you have seen in the example, you have just seen about what is the sequence length and what was the vector, that is embedding dimension. But as you move, as you increase your size of input, you will also have one more dimension coming, which is your batch size. When you have large amount of sentences given, sentences will be passed as batches. Okay. An example is given for a batch size 2, sequence length 4, embedding size 100. The output shape will be 2 by 4 by 100. So it's a 3-dimensional tensor that you get as an output out of a word embedding. Okay. Now, As I told, the embedding layer is also trainable, meaning it learns to assign optimal vector representation to words during model training. Try to understand what is this embedding layer. Embedding layer is also one of a kind of neural network. Even if you are taking a pre-trained embedding network into your model, it is also a trainable neural network. See what is happening. Here, the idea is completely different. You'll have to use little of your mind. Now, we are working with text. Let's say our model that we are designing is trying to predict the next word that is coming into picture. Okay, so what do? First, you will create an embedding layer to create your embedding matrix. Then you create your LSTM model. Then you try to predict the output. That's it, finished? No? What? Is it correctly predicting? Is it not correct? How much is accuracy? How much is loss? Again, what you will do? Back propagation. So back propagation, what is happening? You will update your weights and bias with respect to your LSTM model. There is a chance also that these are trainable layers. That means whatever embeddings that you have done, you can also actually check and correct that so that it can improve the performance of your model. Are you understanding? So this is like an upper hand over what you have learned so far. Feed forward, feed back. Now apart from that, embeddings. Understanding? Yeah. So embedding layer is trainable. It learns to assign optimal vector representation, optimal vector representations, okay, to words during model training. This you will not be doing from scratch. You have ready-made libraries that helps you to do that. We are trying to understand how it is doing. You're not supposed to do, you will not even realize the vectors got updated. You'll just see that, okay, my accuracy is improved. How did it improve? Because even vectors are getting optimized internally. You have to understand in that way. Okay. So, you will have, you'll start with a random or a pre-trained vectors, which is your initial embedding matrix. Second step, you will be training with the loss function. For an example, if you're training for sentiment analysis, the model adjusts the embeddings to better separate positive and negative. Gradient updates, same, during backpropagation, embedding vectors are updated along with other model weights. That's what I just told you. So it's a little bit upper hand model than what you have been learning throughout. Clear enough, guys? This is how it is going to achieve. Now, coming back to this slide, I told you I'm going to explain you a bit on working of RNN and LSTM. This was a wrapper, embedding layer was a wrapper. The next side would be the model creation. It could be an RNN model or an LSTM model. So the first prerequisite remains the same, wherein you are converting your text data into word embeddings. How it is done, I showed you. Then once you have got those, machine readable vectors in your hand, then what happens? Then as I told you, these sequences of words are processed one by one, wherein previous hidden state is passed to the next step. So this is creating your short-term memory. Till here, RNN and LSTM both are same. Here I told you one important point in my introduction. I told you RNN faced a problem because there were chances it had exploding gradient descent. So here if you introduce in an RNN cell a TANH activation function, somebody answered me that, TANH activation function, then it will be helping you to regulate that explosion. Why? We will see. So hidden state, when you calculate, as I told, I think I need not explain this again. Hidden state is calculated through what? Hidden state of the previous timestamp, current input, and then you calculate the next state prediction out of it. Alright, now I was talking on this. Why TANH activation function was important? It is a squishing function which helps you to, what is the limit of TANH? -1 to 1. So whatever output is coming, if it is squishing between -1 and 1, then there is no chance of having, explosion of gradients. Okay. So information vectors undergo various mathematical transformation. Some values can explode in this process. causing the other values to be insignificant. Thus, tan h will be helpful to regulate it between -1 and +1. So now quickly coming on the major part, which is working of LSTM now, guys. LSTM stands for? Till now we have seen only short-term memory. Now we have to understand what is this long-term memory. So long-term memory mein, am I storing everything from previous data? What am I storing? Important words, keywords. Okay. So now LSTM has similar control flow as an RNN. It processes data sequentially, passing on the information to propagate forward. Major difference will lie what exactly happens inside LSTM cell. So what makes LSTM special? It can achieve long-term dependency. It knows which information to discard or retain, but how does it achieve? How does it achieve? So it can achieve using two things. One is a gate, another is a cell. I already told you. Gates are of how many types? What are they? Input, output, forget. And the cell that holds that memory, we call that as memory cell. So this is an LSTM cell. All of you just have a look. How many parts it has been divided into? Can you read? 4. Input gate, output gate, and forget gate, and what is this cell state? Long-term memory. Okay, so that's how the name long, short-term memory. Clear enough, guys? So with that architecture, now you should understand the long-term memory is actually coming through that cell state. And what is helping that create that long-term memory? Which word is important? Keep that keyword to the memory. This word, the, a, and are irrelevant to us. We are supposed to forget that, discard that. What is doing that? The gates are managing. How they are managing, we will see. Clear enough with the architecture, how things are going in LSTM? We'll move forward. So cell state actually acts like a sequence highway which transfers the relative information down the sequence chain. It's like the main memory of your network. Cell state can transfer information from previous time steps as well. Thus, it reduces the effect of short-term memory, as I discussed. Information can get added or removed via the gates present in the cell. So, what are these gates? They are also some processing units, no? So, these gates are also neural networks only. Okay, you are just using those modules into your coding. Internally, they are also the neural network. Clear enough? So, gates are a kind of neural network which are going to decide which information to retain or discard onto the cell state. Gates are trained to learn which information to retain or to discard. So, it's like a neural network. Suppose it's a forget gate, for an example, and a word is coming like I, insignificant, discard. Happy, significant, keep, pass that to cell state. Okay, so forget gate is deciding, it's a neural network, it can decide. It will decide which word is significant or insignificant, which requires forgetting, which requires keeping. Input gate actually helps to keep and append things to cell state, which is your main memory. Output gate is out of that cell state, now what am I supposed to predict as my output? Understood? Clear enough? So these are all neural networks that are doing their own job. Clear enough? Now, hidden state in LSTM is there, yes, but now it is broken into two parts. The first is a cell state, which we call it as a memory of your cell, where all the information is stored. And second is again a hidden state, like a normal RNN hidden state, which is used for computing your output. You have to remember one point here, that cell state and hidden state both are shared across every time step. Okay. Now, talking on gates, gates contain sigmoid function. Why? Because it is able to squish your value between 0 and 1. And that helps you to actually decide retain or forget. Okay, retain or forget. So, thus the network learns which data to remember and which data to forget. and there are 3 gates that we are going to discuss about LSTM in detail. The first one is the forget gate. So what do you think will be the activation function associated with the forget gate? Sigmoid, because sigmoid is between 0 and 1, and this is your first step in our LSTM, where we are going to decide which information you are going to throw away, which information you are going to keep. That is forget gate layer. So what does it do? It is going to check for the previous layer, state, that is hidden state, h of t minus 1, and current word x of t, compares both of them, understands whether the new word as an input has to be kept or to be forgotten. So if forget gate output ft is 0, means you are supposed to forget this information. If it is 1, that means you have to, but that is done by some other gate. This only decides whether it is capable of forgetting or keeping. Clear enough, guys? So ft will be the output of your forget gate. For an example here, let us say we are training an LSTM with the next word prediction, and the sentence is, hi, my name is Alice and I love to play. So hi, my name is, all these are insignificant. So a forget gate will forget all these things. But when it comes to Alice, it is a subject of your sentence, so it has to keep it. Are you understanding? So for hi, ft will be 0. You have to forget it. For Alice, ft will be 1. You have to retain it. Are you understanding? Yeah. So forget gate equation is this, wherein you are using a sigmoid function to the previous state and the current input. If ft is 0, means you are forgetting this information. If ft is 1, then means you are retaining this particular information. Clear enough? Next gate, very crucial, input gate. So what is an input gate doing for us? The input gate decides how much of new information should be added to your memory. In this case, let's say if the next word is play, it is insignificant. So input gate actually, it is significant. The input gate evaluates how relevant is it for updating your memory. Okay, and then the LSTM already has the phrase Alice and I love to, and then Alice is kept in main memory. Okay, and I discarded, love, emotion kept in main memory, to discarded, play kept in main memory. Alice love play. Predict the next word. It could be guitar, it could be cricket, it could be anything. Understanding? That's how a model works. So now what is happening here? Play is useful because it is something relevant to Alice that he or she loves to play. So the input gate adjusts the memory by adding more detailed information about what Alice loves to do. So the next thing, it will be now focusing on what is coming next. Okay. So here there are 2 equations that I have written over there for input gate. See, mathematically right now not that significant, but for your understanding it is important. What it will do, it has 2 parts. The first layer is sigmoid layer, which will decide the values that we will update. New information taken from the forget gate, that is to be added to your cell state. And second will be a tanh layer. Why do you require? Because you require to create a new candidate vector that is now entering inside your memory. Yes or no? So here you will be having 2 things. One is a candidate state and next is an input gate output. Okay, so input gate output tells, okay, this is the particular word that has come from forget gate. It had 1 in it. That means it had to be input to your memory, and I have to create a new vector for it as well. So that's how I of t and c dash of t. Clear? So forget gate it tells only whether to keep or not. Keeping it into your cell state and determining a new vector out of it, it is all done by the input gate. Clear enough? Next. Okay, there was this one example where I want to just tell where it is functioning. Like Mark is a good singer. He sings really well. So he is now related to whom? Mark. If I add one more sentence, Jacob sings really well. He is also a good singer. So now he is representing whom? Jacob. So all these additions and deletions are now taken care by forget gate and input gate. Clear enough? Subject of the sentence is changing. So that change now, discard mark and keep Jacob has to be told by forget gate and then implemented by input gate. Create a new candidate vector for Jacob. Clear enough? Yeah. So now it's time to update all cell state CT minus 1 into CT, and for that you have to multiply previous cell state CT minus 1 with a forget gate output also. So forget gate output also, if it is 0, previous memory is lost, new memory is created. Clear enough? Now what is the next one finally? Output gate. So output gate will decide what we are going to output. This output will be based on our cell state, but it will be a filtered version. It will be a filtered version. Why? Because we will first run a sigmoid layer which decides what part of cell state we are actually going to give an output to. Okay, so that's how this is your output gate architecture. We put the cell state through a tanh function and multiply it with the output of sigmoid gate so that we can only output that particular part of your cell state that we actually want to give it to the output. So apart from sigmoid, you will also use tanh inside your output function. See, I am not diving much detail into the mathematical formula and all the stuff because they are readily made module for your coding, you will be using it. But for you, it is important internally also how things are happening. So till now, I am sure you were not aware that RNN mein na, there is something like embedded vector which is also getting changed to get you correct predictions. They can be made by you, there will be pre-trained, apart from learning rate, there is some other hyperparameter that could affect your model. All these things were not known to you. So we are diving in detail just for the benefit of your model. Clear enough? So next time, say, suppose if there is something in accuracy, you think everything is correct, what you will do? I remember embedding size also is crucial. So you'll go back, you'll change your embedding size in your code and try to, rework on your model. So things like that are important. So that's why I'm not much diving into mathematical function, but yes, if you are really keen enough to understand, you come to me, I'll explain. Okay? So, as I was explaining, let's see an example. The output gate determines what part of updated memory should be sent out as a hidden state, which will influence the next word prediction. After the forget gate has decided which information to forget, input gate has updated the memory, output gate looks at the current state of memory and decides which parts to the output, which part is given to the output. So, the output gate focuses on the most relevant parts of the memory. For an example here, what is the most relevant part? Alice, love, play. 3 words. Remaining all were discarded, right? Alice, love, play. Predict the next word. It could be, and now the model has to see, it's already trained by some value. It is predicting. How well it is predicting? It can write soccer, it can write guitar, it can write chess. It will predict something and some value will come as an accuracy. You will rerun that particular model and it starts predicting, it predicts till that entire loop of forward propagation, backward propagation keeps on repeating until you get an optimized version of your output. Clear enough? How textual data is now giving you output with entire accuracy and prediction. This was our entire process. So, today what we have seen was what were the shortcomings of RNN. What were the shortcomings of RNN? Major was vanishing gradient descent, with which it got its name as short-term memory, because when the information was too long in text data, it was not, or sequential data to be precise, it was not able to retain that much amount of memory. Why? Why it was not able to retain? Because learning was not happening in the initial layers of RNN. Why? Because of vanishing gradient. Clear enough? What was the solution to this problem? Long short-term memory, LSTM. Short-term memory in an LSTM is provided by dash. Hidden state. Long-term memory? Cell state. Clear enough? What exactly is present inside an LSTM cell? What type of gates? Input gate, output gate, forget gate, and there is a cell state also. What exactly are these? They are interconnections of these neural network. Technically speaking, 4 neural network are chained together inside one LSTM cell. Okay, so now these gates are also like neural network that they are processing. Okay, now very important. Does machine understand that sequential data that you are giving? What does the machine understand? Vectors, numericals, again that numericals for sure. So numericals, so what you have to do, sequential data has to be converted into vectors. What is that process called? Very good, word embeddings. Okay, sometimes you can call that as an embedding layer also. So what is happening inside that embedding layer or word embeddings? Tokenization is happening and several steps are there which we will see. And embedding matrix is getting created. What is the size of embedding matrix? Vocabulary size by length of embedding dimension. Dimension of your vector. Are you clear? Okay. What is the output of an embedding layer? If I am talking on LSTM, let's say. What is the output of an embedding layer or an embedding word embedding? What is the output? Vector hai? Tensor. What is the size of that tensor? Why do you have to give batch size? Multiple sentences are given as an input, batches. So what is the output size? Batch size into embedding dimension. Clear enough? So that was our overall embedding part, embedding layer. Then we dived into architecture. What did we see majorly? First gate was forget gate. What does it do? It decides. It decides which information is to be discarded or which input vector that is coming is to be discarded, which has to be retained. It decides. Okay, and then appension to the memory happens through input gate. Input gate mein what is happening? You are adding any new content to your memory and also creating a candidate vector for the same. Okay, and then through output gate you decide which output should be coming, which should be taken through your LSTM cell as a prediction. For an example, if the application demands prediction. Okay, clear enough? What is the major role that is happening over here? Cell state is doing the major role. What does it do? Stores the keywords or stores the relevant information with the help of input gate. So, hi, I am Alice, I love to play was the example that I told. So, hi was discarded, I was discarded, am was forgotten, Alice was stored into your cell state. I discarded, will discard, I love was an emotion, so it was stored. So, now the cell state had Alice, love, 2 was discarded, play was kept. So, Alice, love, play was there in your memory. So, as per the context, you will, as an LSTM will predict the output. It could be any verb because it looks like, loves to play. Play is a hobby. So, that, what type of hobby it could be, contextually it will be able to predict the next word. So, are you now clear how this next word prediction as an example that I taught you is happening using LSTM? Yeah? So, quickly take a break, come back for the quiz and an exercise. Okay? Alright. So, listen to this exercise very carefully because tomorrow you will be doing a hands-on using similar concepts. Okay. So today's practical session that I'm going to discuss is about text pre-processing and word embeddings using PyTorch. Okay. I have already explained you about the theory part involving the embedding layer. Alright. So we are going to quickly see how exactly you will do it on a given piece of data, the text pre-processing, and how would you create word embeddings out of it before you can actually apply it to any RNN model or LSTM model or any other sequential model of your choice. Okay, so very, very important. Just have a look. We'll see a step-by-step implementation. Similar type of exercise you will be doing it tomorrow in your hands-on session. So have a look. The learning objective of this exercise is to understand what are the techniques that are involved in text pre-processing. I have explained about one of it to you today. It was about tokenization. Today I explained you tokenization. What is tokenization? Converting text into tokens. Correct. So converting text into tokens. What are tokens? They are unique words that are present inside your sequential data that you are giving to your machine. Okay. So converting your text into tokens is nothing but tokenization. The second technique of pre-processing is lower casing. Lower casing means what? Converting uppercase letters or capital letters into lowercase. Why is it important? Why is lower casing so important that it is an integral part of your pre-processing of text? Tell. What is it? Because of case sensitivity. Yes or no? If I am writing KMIT all caps, capital K, MIT all small, KMIT all small, all three of them will be treated different, yes or no? Yes or no? So to avoid any type of case sensitivity, it is always better practice to, in your pre-processing, that you involve this step called lower casing, wherein you will convert all your tokens that you are generated into lower case. Are you clear? Then the next step is lemmatization. What is lemmatization? Any idea? Hearing it for the first time? Okay. So lemmatization is converting the tokens that you have generated, words that you have, unique words that you have generated from your text into its lemma. Lemma means root word. Lemma means root word. For an example, if you are writing, say, leaves, there's a word called leaves in your text. Then after lemmatization, leaves will be converted into leaf. Okay. So to understand that semantic relevance properly, you are supposed to break down your tokens into its lemmas. Clear enough? We'll see all of it. And then stemming. What is stemming? There are several verbs which are actually coming with their suffixes and prefixes. Fascinating, ing. Okay. So those suffixes and prefixes, if you want to eliminate, you will perform stemming. So altogether here today we will see these four processes that are a part of pre-processing of your text data whenever you are going to give it as an input. First you will pre-process your data, then perform word embeddings on them, and then eventually you will generate vectors out of it. Then you can give that to your any neural network model like an RNN or a LSTM. Clear enough, guys? Okay. So after you have done with text pre-processing 4 steps today, tokenization, lower casing, lemmatization, stemming, you will also try to filter the stop words. What are these stop words? Stop words are like comma, stop words are like full stop or any blank spaces that are actually of no significance to you. Okay. And then you will also remove any unwanted words of lower significance into your text. Okay, that also can be removed using stop words. Okay, you'll have to basically generate that set of data which you want to put it into stop word and then you can remove it. So as I told, when we saw our example, hey, I am Alice, hey, I am was of least significance. How did the model understand it is of least significance? Because you have actually given them the set of stop words. Understanding. So therein significant words will be chosen, insignificant words would be dropped. Okay, and then what you have, assigning word indices. Why is it important? To create your lookup tables, to create your embedding matrix. You have to convert all these tokens into its indices, and then some basic word embeddings that we are going to see. So all of these, it comes under today's learning objective. So the first thing that I am going to do is data preparation. The first thing that I am going to do is to import the prerequisite libraries that are present in my code. Since you are doing it through by PyTorch, you will import torch. If you are using any NN model, you will import torch.nn. Okay, and if you are optimizing your model, of course you will do, you will import optim. And because you are working now with text data, you will import a library, very important here, called as string. Clear enough? So first we will try to import all the prerequisite libraries required for your code. Second is given input. So here input is text input. I am defining the paragraph that I want to take, that I want to process. So here I am defining a paragraph. So you can see there are multiple sentences here. I have defined a paragraph there telling machine learning is fascinating. It allows computers to learn from data. The more data, the better the learning. Deep learning is a subset of machine learning. You can see the entire thing goes on. You can see it constitutes lot of upper cases, lower cases as well, obviously. Upper cases are also there, and lot of insignificant words like a, the, is, all of these things are present. Significant words are also present like fascinating, machine learning, data, okay, and etc. So this is overall you have to define what text you want to pre-process. Okay. Once you are done that, the first step of pre-processing you will be doing, what you will be doing? Tokenization. So what is tokenization? Tokenization is the process of breaking down a larger body of text such as a paragraph, sentence or documents into the smaller units which we call them as tokens. So word level tokenization is going to split the text into individual words. One example is given over there. The quick brown fox was the sentence, and whereby we have tokenized it into how many tokens? 4 tokens. You can see that the list of tokens, the quick brown fox. Taken all these words. This is word level tokenization. Okay, so the sentence is broken down into individual words, but those words should be unique in nature, that you have to see. Are you clear? Now, let us see how you are going to do a code for it. So, I am going to define here a function for tokenization. So, I have named it as tokenize. I have to pass the parameter as whatever text that I want to tokenize. Once I pass that text, I am going to create an empty list of tokens and an empty string of words. Why? What is happening on the first 2 lines over there? We are defining a function tokenize. It is going to take string text as an input. Here you are initializing an empty list because you want to store all the words that are present inside, your data that is present as a sentences. But then how would you know the word is completed or not? Because it reads character by character, no? So for that reason, you have to initialize an empty string called word here, and I am going to accumulate characters to particularly form a word. First, I am going to check whether a word is completely formed or not. If a word is completely formed, then only I am going to append it to my list of words. Clear enough? Understanding the strategy how I am beginning? Okay. Now what I am going to do now, after I have created empty list for tokens collection and empty string to complete a particular word, I am going to iterate through each character in the input text, and for that I am using a for loop here, and then I am going to iterate throughout my text. And what am I going to do? How do I know that a word has completed its formation? What should I check for? Space. Either space or some full stop. Yes or no? So what I am going to do here is, I'll check if the next character is a white space, like spaces, tabs or new lines, or if at all any punctuation mark like a full stop or a question mark or an exclamatory mark for that essence. Okay, so that means that a particular word has been completed, character by character once you started, and a white space has encountered, it means word is formed, word is completed. Quickly now push that word into your list of words. Fair enough? Yes or no? If you can talk, I can go to the next one. Nah? Yeah? Okay. So this is what we are doing, and checks if the character is white space, and these characters are considered as boundaries. So basically we are checking for boundaries of the words. Now if there is an accumulated word, you will add it to the token list, and then again you will reset your string of word, because again you have to encounter the next word into the picture. So that's what you are doing. If word tokens dot append word, means if word is completed in that string, you append that to the list of words, and then word is again initialized as an empty string to collect another word. Clear enough? Word is a string, checking word is completed. If it is completed, append to the list, empty list that we have got, one word is completed. Again reinitialize that string to 0 to catch up with another word. Clear enough, guys? Yeah. Now what we are going to do? Suppose you have not encountered the boundary. Okay, there is no punctuation mark, there is no white space that is encountered. What do you have to do? That is a character. You have to put it to your string. Okay, so that's what that other sentence is doing. After the loop, if there is still a word left in the word variable, then it adds to the tokens list. Okay, this ensures that a last word is not getting missed. Are you clear with that? So what are we doing? We started with an empty list to store the number of, to store all the words that are present inside your text. You started with an empty string to collect your word going on. How are you collecting your word, guys? By looping through the characters and checking for boundaries. If you found any boundary, that means you got your word. And what you will do? You will append it to your list. Okay? If you are not finding any boundary, that means it's a character. You kindly append it to your string. And the process keeps repeating unless and until you have passed through entire your text and all of your words have been appended onto your list. Clear enough? So that's how a for loop is going to catch up all the words that are present into your vocabulary. Clear enough? Now, once you are done with that, what you are supposed to do? I am doing two things here in this particular step. The first part was tokenization. As I told you, now tokenization is completed. The next part is to avoid case sensitivity. What am I supposed to do to these words? I should pass it through lower casing. Okay, so for that reason, here you can see you can see here I have written word dot lower. So dot lower is an inbuilt method that I am calling, which will convert that word that is present over there that I have extracted into its lower case. So here now I will be printing both of them, the normal tokens that I have extracted out of my vocabulary and the tokens that are present in the token list. Clear enough? Okay, lower casing token list also. So you can see here, these are the tokens that I have captured through my vocabulary. Do you at least remember the first sentence of the paragraph that we are dealing? Machine learning is fascinating. Okay, so you can see machine is treated as a separate token there, learning is taken as a separate token, is fascinating, etc. You can see there crucial, modern, AI, artificial first letter A, they were all caps. Below that, I have now changed them into lower cases through lower method. Clear enough how we have done? Okay, we extracted word by word out of our vocabulary by passing through, iterating through every character, checking for boundary. If boundary is coming, word is over, it will be appended into the list. Otherwise, keep on doing that till you encounter all the words present inside your vocabulary. Once you have tokenized it, convert your tokens into lower cases. So, 2 steps of your pre-processing we have now completed. What is the next step? Very good. It is lemmatization. So, what is lemmatization? As I told you, to convert the tokens that you have got into its lemma. What is lemma? Root word. Okay, so lemmatization is the process of reducing a word to its base or root form called as lemma, while ensuring that the resulting word belongs to the same part of speech. Okay, same linguistic category. For an example, if I take a sentence, leaves are falling off the trees. How many tokens will be generated, guys? How many tokens? 5 tokens. Can you read out? Leaves are falling off trees. So, leaves lemma will be what? Leaf. Are, be. That is, are, was, they are there. Be. Okay, be is the lemma. And falling, fall. Okay, of trees, tree. Plural is converted into its singular natural form, lemma. Okay, so that's how lemmatization process is happening. Clear enough? So now you think about the first sentence that we had. What is it? Machine learning is fascinating. So let's see what is happening. So I want to first go for lemmatization, wherein again I am defining a method, the function there, lemmatization. What would be the input to your lemmatized function? Tokens that you have actually extracted. So to the lemmatized function, I am giving their token, and then what am I doing there? What is present in that lemmas? What is it? Lemmas? What is lemmas there? What is it? It's a dictionary. So that means you have to frame, see, we are doing it scratch. We are not using an automated model, no? We are doing everything from basics so that you understand how word embeddings are taking place. So we are preparing our own lemmas. So how are we preparing? Through a dictionary. What should be the key of that dictionary? Token name. What should be the value of that dictionary? Lemma. Okay. So here, what am I doing? Say learning. What is the lemma? Learn. And computers. Lemma, computer. Data. Plural form, no? Singular form is datum. Lemma is datum. Networks. Network. Like that you can create n number of lemmas and store it inside your dictionary and give it to your machine. Here I am choosing only 4. Understanding? So in the exercise that you will do tomorrow, you will have to create your lemmas and do the pre-processing. Understanding, guys? So you are going to now return back those tokens and get lemmatized token for all those lemmas that you have cross-checked each and every token with. Okay? Each and every token stored inside your list will be cross-verified with those lemmas and replaced with those lemmas if at all encountered. Clear enough with the code for lemmatization? Shall we check the output now? Yeah. So you can see now, can you trace any changes that have happened? Lemmatized tokens we have printed here. What is the change that you can see? Learn. The very first thing. Earlier what it was? Learning. So machine learning became now machine learn. Is fascinating. It allows. Computers became computer. Like that data somewhere became datum. So it is working. So now what you have done, the third step of pre-processing, you have lemmatized your code. Clear enough? What is the next step? Stemming. So what are you doing in stemming? If at all for your lemmatized token or your original tokens, then there's no rule that you should do it only after that. It's up to you. So basically stemming में क्या हो रहा है? You will be removing your prefixes or suffixes if at all any and replacing it with your root word. Okay, without even considering the context of that word. We are not considering context of that word, but we are doing stemming. Okay. So here for this example, stem is the method that I have defined. What is the input that it is taking? Tokens. Okay. Input that it is taking is token. And what are the suffixes that you are going to give? Yeah. Suffix again should be a list of suffixes that you will provide. What are the three suffixes that I have provided there? ing, ed and s. Tomorrow in your exercise you are going to prepare it for your own suffixes. Okay. So for all these suffixes you will check in token if it ends. So for ending ka फिर से you don't have to write a for loop because you are using string library. You are going to make use of that method ends with. Okay. Token dot ends with and you will give whatever suffix that you are giving and then you will return back what you will return back. Suppose if I am giving fascinating as my token, ing is the suffix. It has encountered ing, ends with ing. What it will return out of the token? Fascinate. That means it should first check length of the suffix ing, terminate that part from the last length of your token. Fascinating में से ing it should remove and give me a fascinate. Te नहीं देगा, t देगा. Understanding because context who the hell cares? Stemming does not care, है ना? So it will remove only ing and give the word till t. Clear enough? So what you are getting? Returning the token colon means all the words minus length of the suffix. Code is clear enough, guys? Yeah, and then what are you going to do? Again, you are going to print the token after stemming each and every word throughout your code for which you are using a for loop there. Clear enough? Yeah. So let's see what are the stemmed tokens. Machine is machine. Learning became, is became, why? S was there in the suffix. Fascinating became without any because we are not bothered on context. Clear enough? So this is how stemming works. So you have done the fourth part of your pre-processing. Now important thing. Next step is what? Stop word removal. So what are you going to do in stop word removal, guys? Stop words are commonly used in a language that are usually filtered out during NLP task because they carry little to denote more distinctive information. They are serve only grammatical purpose and they significantly do not contribute anything to the meaning of that sentence, to the context of that sentence. Example, many, is, the, are, an, at, to, etc., etc. Okay, clear enough? So what I am going to do here, again tomorrow you will create your own set I am talking. Create your own set of stop words. List of suffixes, dictionary of lemmas, set of, you must remember this, otherwise कल output नहीं आएगा तुमको, ठीक है? So now what you have got this? You will remove these stop words. I have chosen it is, to, the, from, and, are, at, of, a. So all these are my stopped words and I want to get my filtered tokens out of it. So filtered tokens is a list that what I am passing through now, stemming ke baad I should use this. है ना? So stemmed tokens I am going to use a for loop on which I am going to cross verify this. If this word is present in this particular set, kindly filter it out. Okay. So I am just going to filter it out and print the filtered token. So are you okay to now see the output? What is the filtered output? Filtered tokens after you remove your stop words. So what are the filtered tokens? Machine, Learning, I came because it is not is. है ना? Fascinate, it, allow, and remaining all your stop words were lost. Okay, so that was your next step of pre-processing. Okay, now what are we going to do? This is your actual corpus that you are going to work on. So these are unique. These are unique. Are they unique or not? You are once again going to check. Okay. So, sorry. What makes you talk? Okay. So try to understand, this is a crucial concept. Now you have got word embedding. So word embedding is the first thing that you are going to check. Once again is whatever tokens that you are working with, are they unique? Unique matlab encountered only once. So for that you will use an inbuilt function called set. Once you use set, it will generate only unique words out of the available words. Okay, so for getting unique tokens, you will use of this set method. Okay, so here I am creating my word to vector embedding. I have started. So I have defined there a method called create word vectors. Now here I have to pass on two parameters. First, the words that I want to vectorize, and here my hyperparameter will come. What is it? I will set the dimension of that particular vector. Here I am setting it as 50. Okay, so vector size is 50, passing on to my token. So these are two parameters that I am going to give to my word to vector conversion method. So create word vectors with taking input as tokens and vector size as 50. Now you will, for creating simplistic word vector, you have to make sure all your tokens are unique in nature, for which what I am doing there, I am creating unique tokens out of available tokens, means the tokens which are not repeated, they should be unique words. Now I am renaming it as my vocabulary, vocab. Vocab is nothing but now your unique tokens. You have got vocab, and now for these vocabs, actually speaking, here you will decide if you are going to create your own set of vectors or you will be using any pre-trained vector model like a glove model. Okay? So here I am showing, because it's a very small example, I want to show things how it happens from scratch. We will randomly generate our vectors. Okay, so what is happening in the next step after creating vocab? You are creating word vectors. What are the word vectors created like? They are created like a dictionary. है ना? Lookup table है ना? It's a lookup table, it's a matrix. You should have a row, you should have a column. So that means what? What should be in the row? What should be in the row of your embedded matrix? Vocabulary na, words rana na. So vocabulary will be treated as your rows and individual vectors will be treated as your column. That's how you will define your embedded matrix now. So here it will be done through creating a dictionary. Key will be your rows, which is your vocabulary, and column will be the values for your vector. So how are the vectors generated? They should be generated randomly here, because you are not using any pre-trained model for vectorizing. Understanding, guys? So what I am doing there, word vector is the dictionary that we are creating, wherein the word is my row, and that is I am creating, the word that I am creating here is actually having what? Torch dot rand in the brackets you have got vector size. So vector size we have fixed as 50. So 50 sized randomly generated vectors will be created and will be assigned to your tokens. They will be random in nature. It is automatically generated of size 50. Clear enough? Now what you are going to do? You are going to return your word vectors. And then what you are going to now, actually in the next step, what are you going to do? You are passing your filtered tokens as your parameter there. Filtered tokens le liya. And then if I am not passing anything over there as a second parameter, by default what I have declared as my second parameter in my method? 50. So by default it is taken as vector size of 50. only one parameter here I am passing, which is my token, that is your filtered tokens after your lemmatization and stemming. Clear enough, guys? So out of those things, those words will be taken into rows and 50 sized vectors randomly will be generated using PyTorch. Clear enough? Now, once you have got that, apart from that, you also require, see, word, it will not understand. So, you have to make sure you convert that word into index. So, word to index conversion is needed, for which you already know in Python we have a method called enumerate. So, I am going to make use of that particular method, which is going to give me that exact place, exact value along with its index, that place where it is standing. So, I am going to use enumerate function here to extract index and the word where that index is positioned into a particular dictionary, and then I am going to print that for you. Okay. Now, here we are not printing the vector for you. You can actually print and check randomly generated vector. Okay. So, for a particular token, what should be the vector? You can print and check in your previous example also. You can there print word vectors and check the 50 sized vector that has come. Here, I am just leaving it on you, and then you should be able to see the size, number of words. If you want to see the matrix, it will be like number of words by what? 50. Dimension that you have checked. Okay, so tomorrow you will be doing that in your exercise. Clear enough? After that, here one more step that I have attached here is indexing, wherein you will be converting the words that are generated into indexes. If you want word to index like this, machine is given index 17. Now, why is this important indexing? Because the words which are semantically relevant to each other will be kept nearby. So, here word to index it is done. If you want, later you can change it to index to word also. So, what are we doing in index to word? First we are getting, check here. Word to index me, what are we doing here? Word in enumerate filtered tokens you have got, and you will get through enumerate function directly your position, index. So you got word and position through enumerate function there. You will use this to create your index to word. So what I am doing here? I am converting that into index to word using the items method. Okay, clear everybody. So this is what you are going to do it again tomorrow with some separate prerequisites and some other paragraph, whatever they are going to give it to you. Tomorrow's exercise. Okay, so are you clear with pre-processing steps? What did we do in pre-processing today? What did we do in pre-processing? Tokenization means what? Tokenization means what? Converting the given data, text data into tokens, unique tokens. Okay, that is tokenization. And then lower casing, what does it do? Removes. Why it is converted? To remove case sensitivity. Okay, and then lemmatization, what does it do? Creates lemmas, that is creates root words out of the given tokens. What is stemming? Removing any prefixes or suffixes. So what is and then what else is there? Removing stop words. Any irrelevant words which hold less significant will be removed. Afterwards, what is left to you? The major vocabulary that is present. To that major vocabulary, that is the tokens that are present in your vocabulary, you will perform word to vector embedding. Either you can go for pre-trained vectors or you can generate randomly some vectors of predefined length using PyTorch here. Okay. So after that, you can also go for indexing, for which direct word to index you will be generating through enumerate. or later you can convert that to index to word. So that was a part of exercise that we did today. In our next class, after you come back from your exercises, we will see working with a full-fledged LSTM. Okay? LSTM theory only we did, no? This is just text pre-processing. इसके बाद का we have to build an LSTM model, no? That we will see in our next class, followed it up with attention mechanism. Again, I am telling you, please don't be absent. Everything is sequential. If you will miss this class, you will not be able to cover up the next class. Clear enough, guys? Any doubts if you have got, you can come and ask.